Hello and welcome to the last set of lectures on forces. We're going to be finishing up our discussion of forces by talking about forces that cause a different kind of acceleration, which is the acceleration of changing direction. That is a kind of acceleration. And we're also going to be talking about forces related to objects falling in the presence of air resistance. So both of those things are going to be important topics, and they're going to force us to think a little bit more deeply about what exactly do we mean when we use the term acceleration, and it's going to actually then force us to bring in some more sophisticated mathematical machinery that we didn't use before. We're actually going to start touching on a couple of topics that you really need some calculus for to understand. So this is going to be a great way for us to go from forces, which is this unit, into our next unit, which is kinematics. Alright, so let's get started. And again, a couple things that we're going to talk about: centripetal acceleration and air resistance. So let's jump in and do it. So centripetal acceleration is a different kind of acceleration than what we've studied in physics. We talked about it a little bit last year in Physics 1-2, but we're going to go into a little bit more detail this year, especially since we're doing it at the beginning of the year. And it really goes back to Newton's first law, that if an object speeds up, slows down, or changes direction, an external force is required to do it. And centripetal acceleration is the acceleration associated with actually changing your direction. And in AP Physics, we're going to talk specifically about objects that are moving in a circle. So what we mean is that if you have an object, and it moves in a circle, and it's moving in that circle at a constant speed, never ever changing its speed, but it's always moving in a circle, you actually need a force to make that happen. So centripetal acceleration is the term that we actually use for that circular acceleration. So what happens is, when an object goes around a circle at a constant speed, again, that's what we mean by centripetal acceleration in AP Physics. So we mean the acceleration of going in a circle, just to sort of repeat and reinforce. This is the equation that we use to describe centripetal acceleration. We actually have a with a subscript c, and you'll actually see that in the AP formula sheet, and it equals the square of the speed divided by the radius of the circle. Now, there is a way to come up with this formula using calculus and using some other derivations. For this pass right now, we're going to simply say that this is the formula, and for the next week or couple of weeks, you're just going to memorize this formula and use it. So we will have an explanation later, but for now, I'm just going to say, look, when we have an object undergoing centripetal acceleration, meaning that its speed stays the same, but you notice that it's changing direction because it's going in a circle all the time, use this formula to describe its acceleration. And, of course, to produce an acceleration, you need a net force. That's Newton's second law. And to produce centripetal acceleration, you actually need a constant net force directed at the center of the circle that you're traveling in. So here's a little, it's kind of a bad animation, but it really kind of delivers the point. So I have an object that's moving in a circle, and there's some force making that happen. So the object wants to go straight, and the net force pulls it in a circle. And as it travels, that net force, you'll actually see it change direction as the object moves. See, so that force always pulls it to the center. So the object wants to go straight, and the net force pulls it in that circular direction. So as the object moves around the circle, the net force is always directed towards the center of the circle. It's a really important point for the net force that produces centripetal acceleration. And another thing that we say is that at each instant the object travels around the circle, there is a direction to its speed. And speed with a direction, you remember from last year, is called velocity. And at each instant, the velocity is tangent to the circle. So here's what we mean. So when we're right here, the speed is tangent to the circle, as well as here and here. Now, what do we mean by tangent to the circle? What we mean is that if you were to say, suppose there's a string making the object move in a circle. If we were to cut that string, the object would actually shoot off in a direction tangent to the circle. A really good way to see this is with this little short clip here. So if you look, you're going to see this thing spin in a circle, and you'll actually see when we remove this little tape thing that the object flies off tangent to the circle. So you just kind of watch. It spins, and this is the direction it'll go when we let go. Tangent to the circle, just like that. That's actually so important we should see it again. So it spins, and it'll shoot off tangent to the circle in that direction. So with centripetal acceleration, we're going to basically approach it the way we did before. So ordinary forces produce centripetal acceleration. There isn't this magical thing called centripetal force. You'll hear it used, but I don't like to use that term. Ordinary forces combine to produce a centripetal type acceleration. And for all our demos and the rest of our talk, we're going to be approaching these problems using the same approach we did in all our other problems. We're going to draw a free body diagram, we're going to set the equations using Newton's second law, and we'll use some formulas and solve. So here's a perfect example. I don't know if you've seen this carnival ride or you've been on it, but it's a spinning cylinder thing, and you have a person sort of pinned against it, like you do this picture here, and then it spins round and round and round, and you actually float. So we're given a situation here. We get a coefficient of static friction. That says ms. I should correct that. That should say mu s. So change that in your notes. That's not ms. It's mu s. That weird u thing equals 0.4 when you read that. We've got a radius and we've got a mass. So the first thing is, in this problem, go ahead and read it. We want to find the speed that the cylinder has to spin. The minimum speed if the rider is actually going to be stuck to the wall and not fall. So this seems like a strange question. But again, what we're going to do is we're going to set up by drawing a free body diagram as we did before. So first, as this thing spins, we're on Earth, so we've got the weight of the rider due to the Earth. Now, the reason the rider doesn't slip is that there's actually a force of friction from the wall resisting gravity. In other words, if this wall were perfectly smooth, no matter how fast you'd spin, the person would fall to the ground. We actually have friction with the wall of the ride. Now, the thing that actually keeps the person moving in a circle is the normal force of the wall pushing against the person. And what that force does is it forces the person to move in a circle round and round and round. That's how this thing works. It seems a little intuitive, but these are the forces that actually move. There's no force of motion keeping the person in the circle. There's an actual normal force. So what this means is the friction force opposes the weight, and the effect is that the rider sticks to the wall in one spot. That's the y direction. Now in the x direction, or in the moving the circle direction, the horizontal direction, we have the normal force, and it has one thing that happens. It makes the rider, that's m, spin in a circle so that it's still force equals mass times acceleration as before, but now we have a centripetal acceleration. We're going to actually do a little bit of math in a second. So there's our equations. Let's go ahead and solve part A, where we want to find the minimum speed the rider has to have not to fall when the floor drops. So from the top equation, we solve it, and remember weight is mg, so the friction is actually equal to the weight in order for the rider not to fall. From the friction equation, remember friction is fun, and I've written that using the subscripts of this problem. And we have our formula for centripetal acceleration from before. So now what we're going to do is we're going to take these formulas and substitute them into the top two equations that we had originally. So again, these two equations, we're going to substitute this, this, and this. So let's go ahead. So we now have the bottom equation, and we put in a centripetal is v squared over r, so it's that. And then we do two substitutions. I'm going to substitute friction as mg. And I'm going to use, so I have those two equations right below each of the friction equations. We do substitutions with those and replace the normal force. So what this allows us to do is it allows us to solve. And this is what we get for the minimum speed the thing needs to spin for the person not to fall. Okay, so we do this very much like we did the problems before. What I'm going to have you do in the Google Docs is you will actually go ahead and solve part B in the video. So what you're going to do in class with me is you're actually going to practice solving problems using this approach. So I'm going to actually give you some tougher problems in class, and I'm going to urge you draw the free body diagram, set up the equations, and solve like you did before. It seems different, but it's actually identical to what you've been doing for the past week or two. Now, the second topic I want to cover today is air resistance, and this also introduces some complications. So first, in Physics 1, 2, we always dealt with objects just falling in straight gravity. Now what we're going to be able to do, because we have calculus available to us in AP Physics, is we're going to actually be able to study problems with air resistance, and that's something we're going to tackle both in this class, and it pops up almost every other year on the AP. So the goal of these problems is a little bit different. Before, we just draw a free body diagram and solve for the acceleration. The goal of these problems is to do something a little deeper. We have these forces, and our goal is to determine the position, velocity, and acceleration as a function of time. And that's really the goal of Newtonian physics. If I give you the forces, give me the equations of motion. And again, equations of motion, that means give me position as a function of time. Velocity is a function of time. Acceleration is a function of time. And in this class, we're going to see that there are two types of air resistance we deal with. Linear air resistance, which is when things fall slowly, and quadratic air resistance, which is when things fall a little quicker. So with that in mind, what happens when real objects fall? Well, a couple things. First, the very instant they're released, they fall with an acceleration equal to the acceleration of gravity. And the net force acting on the object when it first starts falling is the weight, and the weight alone. So the beginning acceleration is just plain old g. As the object falls faster and faster, the force of air resistance actually gets bigger as the object falls, and that means the net force and the acceleration decrease. So we're gaining speed with a less and less acceleration. You might need to think about that again. Let me say it one more time. You fall and you gain speed, and yet your acceleration is decreasing, as is your net force. That's something you kind of need to wrap your head around. It's a tough idea, which is why I'm introducing it in words first. Finally, what happens is the force of air resistance exactly balances the weight on the object. And what happens then is the object continues to fall at a constant speed that's called the terminal velocity, and it travels at this constant speed until it hits the ground. So what we're going to do is actually sort of illustrate this. And let me just get a little thing here, and we'll go ahead and actually talk about how this is going to happen. So here's the situation. So I have an object, and it falls, and this is kind of the universal free body diagram. I'm going to have the weight on the object due to the earth, and I'm going to have the force of air resistance due to the air. And here's what ends up happening. We have the weight minus the air resistance equals the mass times the acceleration on the object. Okay, this is how we set up the equation from the free body diagram. Now, what ends up happening is that at time equals 0, the air resistance is 0 because V is 0. And in every case, the air resistance is either going to be equal to, say, some kV when it falls slowly, meaning like a feather or a coffee filter or something like that. Or the air resistance is going to equal to something like negative BV squared when it falls faster. Okay, so here's the situation, and this is why we actually need calculus. I have mg minus, let's say, kV. So we're falling with this linear air resistance, and the effect is the object accelerates. Well, at time equals 0, I'm not traveling at any speed at all. So my acceleration starts off being, my equation starts off being mg minus 0 equals ma. And my acceleration is just gravity, like we said before. What happens as we fall is that this v gets bigger and bigger and bigger. What eventually happens is that we reach a point where we stop accelerating. And what happens then is we have mg minus the air resistance, and the effect is 0. Since we're already moving, we continue moving at a constant speed at a straight line. This is how we achieve terminal velocity. Now, when we have linear air resistance, this means mg minus kv equals 0. So these two forces cancel, and we've reached the condition of terminal velocity, so I'll put a little subscript t there. And we can actually solve for this terminal velocity as mg over k. So what I did kind of here was solve this problem very, very quickly with very little qualitative introduction. That's okay. This is your first pass at air resistance. We're going to talk about this in more detail in class and maybe do a little bit of a lab on it. So I hope this is helpful, and it's a good introduction to air resistance. And what we're going to actually talk about in class is the fact that because we have speed dependent on acceleration and acceleration dependent on speed, the only way we can really figure out what's going on with this equation and figure out what the position and the speed is as a function of time is to bring in some calculus.